Okay, let's be real for a second. Most of us probably think of passwords as just, an annoying string of characters we have to memorize. But in this explainer, we're going to completely transform abstract cryptographic math into a vivid, physical reality. Trust me, it's going to change how you view digital security forever. How did a game of solitaire help build the atomic bomb and secure your email? It sounds kind of like a riddle, right? Well, the answer actually begins back in the 1940s with a brilliant mathematician named Stanislaw Ulam. While he was recovering from an illness during the top-secret Manhattan Project, he was just passing the time playing solitaire. And that simple, everyday game unexpectedly sparked a totally new way of looking at probability and complex problem-solving. So here is our roadmap for today. First, the Solitaire Secret. Second, the guessing game. Third, enter the archer. Fourth, human versus GPU. Fifth, shrinking the target. And finally, number 6, the ultimate defense. Section 1. The Solitaire Secret, a top-secret WW2 breakthrough. Now, at the time, physicists were trying to understand complex radiation shielding, and this was a problem so incredibly massive that traditional algebraic formulas were basically useless. But Ulam realized something amazing. He figured out that instead of doing impossible math, just repeatedly guessing and tracking the results was vastly simpler. I mean, why map out every single possible combination of a solitaire game when you can just play 100 hands and count your wins? He shared this totally brilliant repeated guessing logic with his legendary colleague, John von Neumann. Because their work was highly classified, they obviously needed a code name. They went with the Monte Carlo method, which was famously inspired by Ulam's uncle, who apparently loved to borrow money just to go gamble in Monte Carlo. This specific method, statistical simulation through repeated random guessing, is exactly what modern computers use today to crack your passwords. Section 2. The guessing game. From physics to password cracking. The underlying math really hasn't changed since World War II. We've essentially just swapped out radioactive neutrons for cryptographic hashes. Just like Ulam's solitaire, a brute force cyber attack is basically one massive guessing game. Attackers aren't out there solving some magical math equation to find your password. No, they define the total possible passwords, generate a ton of random guesses, and then track how many shots it takes to get a 50% chance of landing a hit. So the crucial point here is that a truly strong password has about 122 bits of entropy. But what does that actually mean in human terms? Well, it means an attacker would need over 2 undecillion guesses just to have a 50% chance of finding it. And for a little context, an undecillion is a 1 followed by 36 zeros. It is a number so unimaginably large that the human brain literally can't even picture it. Section 3. Enter the archer, a physical metaphor for digital security. Since our human brains can't easily comprehend undecillions of digital guesses, let's translate this into a physical reality we can actually picture. Think of the password as a target. The attacker is an archer, and your security level is simply how hard that shot is to make. Adding characters to your password physically manipulates both the size of the target and its distance from the archer's bow. Let's anchor our metaphor right here to keep things grounded in the real world. Imagine a 50-centimeter bullseye placed on a standard shooting range about 100 meters away. We're using a fixed 50-year period, basically a human jubilee lifetime, as the time frame for our archer to land a single hit. We really want to know, what exactly does a 12 billion 2-bit password look like if the attacker has 50 whole years to just stand there and shoot at it? Section 4. Human versus GPU, scaling the attack. The digital world operates at speeds that make human time feel like it is completely standing still. The contrast is just staggering. Think about a human archer firing an arrow every 3 seconds for 50 years straight. That's a total of 175 million shots. Now compare that to a modern GPU army, the exact kind of massive botnet that real hackers use. That army fires 1 trillion arrows per second. That gives them 1.6 sectillion shots over that exact same 50-year time frame. This shows exactly what happens when an attacker scales up their computing power. So, to keep that standard 50-centimeter target safe from our incredibly slow human archer for 50 years, the 122-bit password forces the target to be placed 0.4 light-years away. Seriously, even though the human is shooting non-stop for 50 years, the sheer mathematical distance created by 122 bits of entropy pushes that target out into the literal cosmos. Section 5. Shrinking the target. Precision versus speed. But what about the GPU? What if we decide to keep the distance fixed at a realistic 100 meters, but we shrink the target to compensate for their blistering speed? Well, to maintain a 50% hit probability over a lifetime, a human at 100 meters just needs to hit a 1.5 millimeter dot. But that massive GPU army, because they are firing so many arrows, to keep the odds exactly the same, their target has to become incomprehensibly small.
That's right, 0.4 nanometers. That is roughly the size of a single molecule. That is literally the only way a GPU firing 1 trillion arrows a second can be kept at bay for 50 years. Your password's complexity forces the attacker to hit a molecular bullseye from an entire football field away.
The attacker does not become a supernatural archer. Their computation power lets them aim at a smaller and smaller bullseye. That quote just perfectly summarizes the math behind cybersecurity. The GPU attacker doesn't break reality, right? They just trade their massive volume of shots for the precision required to hit a molecular target. The more computing power they have, the smaller the target you need to present to them.
Section 6, the ultimate defense, redefining password strength.
So, how do we make sure our target stays molecule-sized? The math gives us what's called a difficulty budget. And it proves that adding length and true randomness to your password directly shrinks the bullseye the attacker is aiming at. If you increase the entropy by adding length, and I don't mean just substituting an A for an @ symbol, but real length, you are effectively changing the physical dimensions of the universe the attacker has to shoot through. Ultimately, what you should take away from this explainer is that you are quite literally using math to push your attackers light years away from your personal data. Password strength isn't just some frustrating IT requirement that annoys us all. It's a structural defense. A 122-bit password represents a generational security horizon. It is designed specifically to outlive a 50-year lifetime of relentless, non-stop guessing by supercomputers. So next time you go to create a password for something important, ask yourself, is your target sitting right at the end of the hallway, huge and easy to hit, or is it floating safely in another solar system entirely? Keep it long, keep it random, and make them shoot at molecules. Thanks for hanging out with me for this explainer, and stay secure.